Welcome. In this lecture, we are going to see a CSTR, continuous stirred tank reactor, also known as MFR, mixed flow reactor. So CSTR or mixed flow reactor, MFR. So let us consider a CSTR in which a first order chemical reaction is taking place. A first order chemical reaction like A gives R is taking place. So let us see what is the equation, differential equation, which will describe the dynamics of this process as well as the transfer function of this process. By the way, this is the question in one of the previous year GATE question paper, GATE chemical engineering question paper, chemical engineering 1995. It is question number 27. This process has been described there in this question, and you are asked to derive the transfer function. In those days, it was the beginning of those beginning period of GATE. In those years, derivation questions were also asked. So this question, CSTR, in which a first order chemical reaction is taking place, was given in that paper, and the question was to derive the transfer function, which we are going to see now. So you can have a look into this GATE paper 1995. It's the same which we are going to discuss now. Well, so a first order reaction is taking place in a CSTR with a constant volumetric flow rate. So Q represents the volumetric flow rate, both inlet and outlet. So we are going to assume that volumetric flow rate is constant, and only the concentration of the inlet, concentration of component A and the inlet Ci and concentration of A in the outlet C naught. So they may change at unsteady state, but the volumetric flow rate remains constant. And this is the first order reaction taking place in a CSTR. So these are the symbols. Ci, I already told you, Ci and C naught. V is the reactor volume. K is the rate constant. It's the first order reaction. So the rate of the reaction will be K into C naught. C naught will be the concentration at the outlet as well as in the reactor. So rate of reaction, first order reaction, this is first order, Kc naught moles of A per liter. So these are the assumptions. First one is there is no change in volume. The flow rate is constant throughout the reactor. So inlet volumetric flow rate is same as outlet volumetric flow rate, and that is equal to a constant Q. The second one, the contents are well mixed, so the concentration is uniform throughout the reactor. Third one, the temperature is uniform and constant throughout. Of course, these last 2 and 3 are the characteristics of CSTR anyway. So CSTR means it will obey these two characteristics represented by this assumption number 2 and 3. So we are just repeating this here, that's all. Well, so as usual, we will write the mass balance in this case at unsteady state. What is the mass balance? We will write the mass balance in terms of moles of A. In terms of moles of A. We will write in terms of moles of A. So rate of moles of A in equal to rate of out, rate accumulation plus rate disappearance by reaction. Everything in terms of moles of A. So rate of moles of A in is the volumetric flow rate into concentration. Ci is the concentration of component A. A is a reactant. So Q into Ci will represent rate of moles of A in entering the reactor. Same way out is QC naught. Accumulation is d by dt of the moles of A within the reactor, that is B into C naught. Plus this is first order reaction. Rate of disappearance is given by first order reaction is this Kc naught. That is moles of A per volume per time. So here for the entire volume reactor, we are writing the mass balance over the volume of the reactor. So the rate of disappearance of A over the volume of the reactor is this Kc naught multiplied by Kc naught multiplied by volume, Kc naught into V. Okay, and this V is constant, so taken V out of the differential sign, and written this. So this is the first equation number 1, unsteady state mass balance. Now we'll write the unsteady state means when there is a change in Ci, and accordingly there will be change in C naught. When there is a steady state, when the CSTR is operating at a steady state, we will write the same mass balance equation in terms of moles of A. Only thing, at steady state we will denote the variables with a subscript S. Ci will be described by CIS. Outlet concentration C naught will be denoted by C naught S. And the CIS and COS are constants. So the same way, rate of moles of A in is this, rate of moles of A out is Q into C naught, and rate of disappearance by reaction is this. At steady state there is no accumulation. At steady state there is no accumulation. Well, this is a steady state equation 2, number 2. Now let us subtract these two equations, steady state and unsteady state. Equation 1 minus equation 2 is going to yield this equation. 1 minus 2 will give you this equation, equation number 1 minus equation number 2. And I will introduce deviation variables, Ci minus CIS, the difference between the variable at a steady state and its variable at unsteady state, and variable at steady state is capital Ci. Similarly, C naught minus C naught S, deviation variable in outlet concentration, is capital C naught. So we'll substitute these deviation variables in equation 3. If you substitute this in equation 3, you'll get this Ci minus Ci as a substituted Ci, C naught minus C naught S as substituted C naught, and this is V dC naught by dt plus Kv into C naught. So you get a first order ordinary linear differential equation. So this is a first order ordinary differential equation which will describe this process. This equation describes the process, dynamics of the process at unsteady state. When there is a change in inlet concentration, how the concentration in the reactor changes. Now once you get the differential equation, getting the transfer function is easy, simple. The usual procedure: take Laplace transform. Take Laplace transform of the given equation. Take the Laplace transform of this differential equation. Ci and C naught, remember, they are functions of time. So Laplace transform of Ci is Ci of S. Similarly, LT, Laplace transform of C naught is C naught of S. This is the first derivative. Differential is this is Ci, transform of Ci, this is transform of C naught, and this is the transform of the first derivative, S into C naught S plus C naught 0, and this is Kv into C naught S. So this is after taking Laplace transform of this differential equation. Now this C naught at 0, so this is the deviation variable at 0 time. Deviation variable is C naught minus C naught S. At 0 time, at t equal to 0, both were equal. C naught is equal to C naught S. Only after t0, after t equal to 0, then only the variable changes. So at the beginning, at t equal to 0, the deviation variable is 0. So you make this as 0 and simplify the remaining terms. So C naught 0 is made 0, is 0 substituted 0. The remaining term Q plus Vs plus Kv. And you rearrange this and find what is C naught by CIS, C naught S by CIS. C naught, remember, this is the output concentration. C naught is output concentration and Ci is input concentration. So the function relating this C naught and Ci in terms of Laplace transform variable will be our transfer function. So C naught S by CIS, remember these are deviation variables, capital C naught and capital Ci. This is capital Ci, this is capital Ci. will be equal to this Q by this, and I can bring it to the first order form K by tau s plus 1 by dividing the numerator and denominator by Q plus Kv. If I divide the numerator and denominator by Q plus Kv, I am getting this, which is of the form which is equivalent to K by tau s plus 1. This is the standard first order transfer function. So you find that the process taking place in a CSTR, that is a first order reaction, first order chemical reaction taking place in a CSTR, its dynamics can be represented by a first order transfer function with the gain K equal to Q by Q plus Kv. Q is the volumetric flow rate, V is the volume of the reactor, and K, small k, is the rate constant. This is the rate constant K. This K is gain. Capital K is gain and small k is rate constant. And the time constant is tau equal to V by Q plus Kv. If you substitute the dimensions of Q, volumetric flow rate, Kv, you will find the time constant has got dimensions of time, maybe second or hour or minute. And if you substitute the dimensions here, Q by Q plus Kv, you will find that this does not have any dimension. K, this guy gain K is dimensionless. Gain K is dimensionless because it relates both the variables are same, outlet concentration divided by inlet concentration. So the ratio of the denominator and numerator have the same units. So the gain which relates these two also does not have any unit, because C naught by CIS, the net dimension of C naught by Ci is nil. So K has no dimension. So this is a first order transfer function representing the process of mixed flow reactor or CSTR with a first order chemical reaction. We will see more examples in the subsequent lectures. Please stand by for those lectures.